I am going to present the result of a study about the numerical modeling of the failure mechanism of a titanium silicon carbide metal matrix nanocomposite subjected to hypervelocity impact. This work is the result of an ongoing collaboration between the University of Nevada, Las Vegas and Politecnico di Milano. Resistance to hypervelocity impact of an external object is a design requirement for a spacecraft, since it may collide with micrometeoroids or orbital debris at speed of several km per second. Titanium alloys are extensively used in the aerospace industry due to their excellent properties, in particular high strength-to-weight ratio, good corrosion resistance, and high melting temperature. Impact resistance can be improved by deposition of a titanium silicon carbide metal matrix nanocomposite coating. For this reason, the aim of this study is to develop a numerical model for predicting failure of the metal matrix nanocomposite coating, using the smoothed particle hydrodynamics technique. Impact resistance has been widely studied in the literature. Schoenberg, in 1990, found that the extent of a damage to a dual-wall composite structure depends on the material properties of both the projectile and the structure. Several authors developed numerical models based on the SPH technique to simulate fragmentation of metals when subjected to hypervelocity impact. Zhang et al. Found that titanium silicon carbide metal matrix nanocomposite coating exhibited double hardness with respect to the titanium 6,4 substrate and decreased the friction coefficient. Consequently, wear rate was reduced by 78%. The authors themselves performed hypervelocity impact tests on coated titanium 6,4 and found improved impact resistance. The aim of this work was of developing a numerical model for predicting failure of the titanium silicon carbide metal matrix nanocomposite, exploiting the SPH technique. The results of the hypervelocity impact test already performed by the authors in the earlier study are exploited in this work. Using selective laser melting, a titanium silicon carbide metal matrix nanocomposite coating with a thickness of 200 microns was deposited on a titanium 6,4 substrate. In this study, parametric studies were performed to assess the influence of the material model input parameters on the shape of the crater generated by the projectile. In this way, it was possible to better understand the phenomenon and increase the accuracy of the numerical model. The experimental apparatus is shown in this slide. Pure titanium powder with an average size of 45 microns was mixed with 5% weight silicon carbide nanoparticles, which has average size of 40 nanometers, using a ball milling for 4 hours, without a protection atmosphere. 200 microns of the mixed powder was deposited on the titanium 6,4 plate, which has a thickness of 12.5 millimeters. Afterwards, the surface was processed with selective laser melting. The experimental apparatus in the University of Nevada, Las Vegas is shown in the figure on the right. Hypervelocity impact test was performed using a two-stage light gas gun. The projectile was a Lexan cylinder with a diameter of 5.5 mm, a length of 8.6 mm, and a weight of 0.25 grams. The impact velocity varied in the range between 3.7 to 5.4 km per second. The cross-section of the uncoated and coated specimen is reported in the figure on the left for different impact velocities. The crater diameter and depth was measured, and it is reported as a function of impact velocity in the diagrams on the right. Both the crater diameter and the crater depth increase if the impact velocity increases. In particular, the crater diameter was fitted with a linear relationship, while a second-order polynomial was used for the crater depth. From these diagrams, it is possible to notice how the impact resistance of the coated specimen is higher, since the crater depth at the same impact velocity is lower. The numerical model was developed in the software LSDyna version R11. An axisymmetric model was preferred over a three-dimensional model to save computational time while keeping acceptable accuracy. The smoothed particle aerodynamic technique was used for the discretization of the three parts of the numerical model, which were the projectile, the coating, and the substrate. No boundary conditions were applied to the edges of the target, since it is an hypervelocity impact and the results are not dependent on the condition far from the impact region. Three different models were developed with different particle spacing. The final choice was the one which is displayed on the figure on the right, which had better accuracy in the prediction of the experimental results. The Johnson-Cook material model was used for the simulation of the material response of the Lexan projectile and the titanium 6-4 substrate. This material model takes into account strain hardening, strain rate hardening, and thermal softening of the material. It is therefore well suited for the simulation of the material response under the condition of hypervelocity impact, where there are high strain rates and local heating. It was not possible to find Johnson-Cook parameters for the coating. Therefore, it was used the bilinear plastic kinematic material model. The baseline values for this material model were selected from the 35% volume silicon carbide, and the material parameters are reported in the table: the elastic modulus, the Poisson ratio, the yield strength, the tangent modulus, and finally the failure strain. In particular, this material model is based on an element erosion criteria which delays the element once the strain is higher than the maximum equivalent plastic strain, which is defined by the user. The results of the simulation are reported in this slide. The Lexan projectile is completely destroyed during the impact, while the damage on the target is localized in the impact region. Upon impact of the projectile, a compression wave starts propagating in both the axial and radial direction. At 0.4 microseconds, most of the titanium silicon carbide coating particles are eroded. At 0.6 microseconds, a crater starts to form. As the impact progresses, a bulge is forming on the backside of the target. A parametric study was performed by varying each single input parameter in the range between -10 and +10%. The crater volume was computed using the formula displayed in the slide, and thus also the error with respect to experimental data was calculated. It was found that if the elastic modulus increases, the crater volume increases, and thus the error. This consideration is also valid for the Poisson ratio, the yield strength, and the tangent modulus. Instead, if the failure strain increases, the crater volume decreases, and thus the error. The same results are here reported in a table. If we consider the baseline set of input parameters, the error is of 7%. We take into consideration the elastic modulus, the Poisson ratio, the yield strength, or the tangent modulus, we obtain the least error by decreasing this input parameter by 10%. On the other hand, if we consider the failure strain, we obtain the least error by increasing the parameter of 10%. This is also the configuration with the least error, which is lower than 1%. On the other hand, the highest error is obtained by increasing the Poisson ratio of 10%, obtaining an error of 11%. The previous results were obtained for an intermediate impact velocity. We can consider the set of parameters with the least error, so the one with the elastic modulus, Poisson ratio, yield strength, and tangent modulus decreased by 10%, or with the failure strain increased by 10%, and evaluate the error by changing the impact velocity. As shown in the diagram on the right, The error increases if the impact velocity increases. The same results are here reported in a table. Also, another set of parameters is considered, reducing the elastic modulus, the Poisson ratio, the yield strength, and the tangent modulus by 10%, while increasing the failure strength by 10% at the same time. This new set of parameters lead to very small error, but again, the least error is obtained by only increasing the failure strength by 10%. The results of the parametric study are finally summarized in this slide. The best set of input parameters is obtained by keeping the baseline values of the elastic modulus, the Poisson ratio, the yield strength, and the tangent modulus, and by increasing of 10% the value of the failure strain. This set of parameters lead to a very low error on the cutter volume. This error is below 1% for all the impact velocity except for the highest one, where it is 1.2%. The variation of the error between the worst and the best configuration is of 0.5%. The conclusions of the work are reported in this slide. Failure mechanism of a titanium silicon carbide metal matrix nanocomposite coating subjected to hypervelocity impact was shown. The sensitivity analysis was performed starting from the parameters of the titanium silicon carbide metal matrix nanocomposite coating with 35% volume silicon carbide. It was shown that by increasing the failure strain by 10% while keeping constant all the other input parameters, the accuracy of the numerical model was improved. And finally, the usage of a bilinear material model for the metal matrix nanocomposite coating was justified. And this is the end of the presentation. Thank you for your attention.